Hi, this is Manuel, Delta Lima 2, Mike Alpha November. Welcome back to my channel. You have decided you want me to talk a little bit about antenna building, so we are going to do that today. If you have seen my last video, I will put you a link up here. You have probably seen me using this improvised endfed half-wave antenna. And when I did a little bit of securing, I touched the core and realized this got pretty warm. And I claimed further that it could be prevented if you just used bigger core material. In fact, I do not know that. I am aware of the fact that other people using bigger cores say it doesn't get warm, but how much energy is really dissipated in those kinds of transformers, and how much is it dependent from the kind of core size we are using? The ultimate goal around this series of endfed half-wave antenna videos will be to figure out whether the size of that core material is responsible for the losses we've seen, the heating up, or maybe it's just always the same loss, but we don't see it. Imagine half watt dissipated in here will be felt as more heat development than a half watt dissipated in here. Maybe it's always the same and we just can't recognize it. That's the goal of this video series. However, in this part 1 of this video series, we are going to talk about the endfed half-wave theory, how it works, how it should work, the broadband transformer, how it's being built, how it works, and how we can confirm by measurement the theory. So I think we need to talk a little bit about the core element of every endfed half-wave antenna, which is this broadband transformer. Let's jump right in. I've drawn a little schematic of the endfed half-wave. This is our antenna connection where the transceiver is being connected. We have here a capacitor that will help with lowering a little bit the SWR over a broader range of frequencies. We have a primary and we have a secondary winding on the transformer. This is indicating that it's on a core. The primary has 3 turns, the secondary has 21 turns. This makes a ratio in terms of windings from 1 to 7. The same is valid for voltage. This means if you apply 1 volt of AC here, it will end up with 7 volts of AC here. That's the voltage transformation ratio. And impedance transformation is 1 in 7 squared, which means 1 to 49. In our practical application here, this means when we connect 50 ohms on this side, it will end up with 2450 ohms on this side. As you can see, here will be the antenna wire connected, and this side is completely connected together and on ground. How do we get from this to this? As you can see, the first 3 windings are twisted. We are basically the first 3 turns of our 21 turns and of our primary are wound together. And then we have following that 18 turns, 18 additional turns. I'm going to show you in detail how it's being done, but this is the theory around that. And I'm going to show you in detail what it does and what's the effect of it. So let's talk a little bit about the variations of this pattern. When you look through the internet, you will find a lot of instructions that will tell you to use 2 turns and 14 turns, which is a valid thing to do. It's also a 1 in 7 ratio transformer that will end up in impedance transformation of 1 in 49. And especially if you're using bigger core, you might get away with that. However, when using those smaller cores, the XL that 2 turns are creating are a little bit on the low side. XL is inductive reactance. So I decided I would go with 3 turns, 3 in 21 turns, as you do not have much of a disadvantage anyway using 3 in 21 turns, except for you using a little bit more wire, which means a little bit higher DC resistance, so a little bit lower Q. I hope I get my point across. So if you use 3 in 24 turns instead, for example, you would end up with a transformation ratio of 1 in 8 or an impedance transformation ratio of 1 in 8 squared, which would be 1 in 64. You probably read that as well. And this is also recommended, but that's a very academic thing because it depends on the elevation height you put your antenna to. We are most likely using our setup in a QRP portable operation, which means you won't elevate your antenna so high that this matters. So you're on the safe side with 1:49 transformation ratio. Anyway, I found this ratio to work for all applications. Sorry guys, we are not through yet. I need to torture you a little bit more about theory. And by the way, I have no clue about the theory. This is how I explain it to myself with my layman's terms. So if there's an expert out there, please don't kill me for that. I'm trying hard here. This is lambda half of lambda. In case of 40 meter band, this would be around about 20 meters. Doesn't matter for here. I hope everybody knows what lambda is, the wavelength. Now, everybody knows a dipole. Dipole is basically a center-fed half wave. And if we now go to this drawing here, there I tried to show you a little bit about the current distribution and the voltage and or resistance, impedance distribution along that wire while being resonant or while resonating. So if we look at that, when we go to the center, in the center we have low resistance. We know that. We have around about 50 ohms here. And we have also low voltage while there's very high current flowing. When we go towards the ends, this is reverting. We are having more voltage and more impedance, resistance, and very low current flowing. And from those two curves, we can see that we need to feed at the end point of our half wave. If we want to feed there, we need to have very high impedance. Sorry, this actually should be Z, not R, sorry. So feeding a half wave not in the center like on a dipole, but on the end requires a high impedance. And this is where we need our impedance transformation. That's how that works. I hope that is clear enough. Finally, let's start with the practical part here. Okay, so I'm going to show you how the winding pattern goes and how to make the transformer. Let's just put that to the bottom so that I know what you can see and where I need to move my hands. I'm having here copper enameled wire. In that case, I think I'm using 0.5 millimeters in this case, because it's still a relatively small core. And I have round about 1 meter here. I will probably end up with a lot of remaining, but that's better than realizing you have not enough when you're almost at the end and you need to redo everything. So what I'm doing here, I'm just like measuring 20 centimeters, making a loop here. So it looks like this. Then I'm starting to twist the ends, like so. And trying to do that as constantly as possible, so we will end up with a relatively constantly twisted wire here. I've seen many techniques how this is done. Some people even use power tools for that. I don't see the necessity. Maybe I'm going to use them for later when I'm doing a lot of them. But this seems just to work. Now twist it, twist it, twist it until you feel you have a sufficient length there. There you can see that's already a problem, because there's just one wire wound around the other. So I'm needing to pull a little bit more. Okay, I think that's enough. Maybe. Okay. Not too pretty, not too good. But this will do the trick and you get the idea. What I'm doing now, I'm putting through the winding through the core, and just to make you aware of that, this already is our turn number 1. You see I have the loose end and the long end on the bottom. I'm sticking my core over that. I'm making sure I'm resting the space where those two separate on the bottom of the core. And then I'm making my second turn, 2 and 3. So now we have the 2 wires that we twisted together 3 times passing the center of the core. This is our first 3 turns. And this is, by the way, we did now the first 3 turns for the 50 ohm side and the 2450 ohm side together. This is total 3 turns of primary and the first 3 turns of secondary. And now where we split up, we have the exit point. We already have now both ends of the primary side here. This twisted side is the ground side. This is the common side for both, as you can see. This is the input side. And now we are going to continue here. So we finish the 21 turns. Remember, we are already at count number 3. So our next will be 4. Yeah, 4, perfect. 5. 6. 7. By the way, in order to make that thing work really good, it's important that the windings are close to the core. 7. 8. I suddenly realized that it's probably really a little bit too long because it's not very practical to handle so much wire. 9. And while focusing on the core, I need to make sure you see everything. 10. 10. Now, let me show you something. There's several ways we can continue now. This is our input, our primary, and there will be our secondary. I could now continue simply winding all the remaining turns and would end up here. So we would have input side here and output side here. And there's now another possibility where we just go through and wind the rest here. So we have input side here and output side here. This is what I'm going to do. We have now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 turns. And we need 21. So either I wind an additional one and make the transition then, or you can do that then now and wind another 11. It doesn't matter. I'm going to do now my 11th. And then going to make the transition. By the way, people are also arguing whether going through here counts as a turn or not. I don't count it. I have 11 now and start with continue with 12. Come on. 13. 14. 15. 16. 17. 18. 19. 20. 21. That's it. This is how it's being done. It's not the nicest transformer I've ever built, but since I'm doing that on camera and I need to watch my time, this is not bad at all. Okay, I cut it here, the remaining wire off, cut those two ends. That's our endfed half-wave broadband transformer. Now let's connect that thing to the nano VNA and have a look at what it does, if it already works perhaps, and we can see what's going on. Let's go through one more final time. This is the common side for primary and secondary. Both primary and secondary have 1, 2, 3 turns. Then the feeding side of the primary is put out, the secondary is continued, 4, 5, 6, 7, 8, 9, 10, 11. Then we are going over 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. That's it. 6 15K resistors in parallel. Should be 2K5. Now I'm measuring in parallel, I guess, my body resistance. It's 2450 ohms or 2.45 kilo ohms. Almost exactly. That's our simulated load, because we have a 1 in 49 impedance transformation. Assuming that on this side we will apply with 50 ohms, we are simulating our 2450 ohms load on the secondary side. The connection is, the input is on the center of the connector here. The common ground is used for both the resistor and the input shield. And on the output we have the other side of the virtual dummy load. By the way, those are 6 2-watt metal film resistors, because I plan to use them also when I apply later 5 watts. Maybe, let's see. It's not necessary. You can also use a single 2K2 or 2K7 with just a 1/4 watt when you just want to look with your nano VNA at it. It's not necessary to have this kind of power resistors. Now let's have a look at the plot. I've set it up at the S11 port, so we are measuring reflection only. Output is terminated with 2450 ohms. And we are measuring SWR. I've set 4 markers at 3.5, 14, 21, and 28 megahertz. So we see we have on 3.5 megahertz SWR of 1.63, at 14, 1.54, at 21, 1.95, and 28, 2.66. Now let's add the 100 pico capacitor to the input, like shown here. I've added here a 100 pico NP0 capacitor rated for 100 volts. For QRP use, that's completely sufficient. When you want to use 100 watts, you gotta obviously, besides a bigger core, or yeah, let's find out in the next videos, but you should at least use those silver micas for 500 volts. That's okay. Now, see how this has changed the SWR. On 3.54 we are now down at 1.5, at 14 we are now at 1.48, at 21 we are now at 1.59, and at 28 we are at 1.33. This has brought down our curve more to the bottom, has helped us to establish a better SWR just using that transformer over a broader range of frequency. This is why we need that capacitor here. Okay guys, that's the end of part 1. I think that's already a pretty long video. Before we wrap this up, I want to say thank you to Tom, Delta Juliet 5 Romeo Echo, who spent so much time over the past years to discuss certain antenna types and techniques with me, and basically what I know about antennas I learned from him. So a big thank you to Tom, much appreciated. And at the end of this day, you should be able to build a broadband transformer, should know how it works, and should be able to just put lambda half here, feed your transceiver here, and be ready to go on air. In part 2, we are going to figure out what core is needed, what core losses are involved, and I hope to see you then. If you like the content, please like, share, and subscribe to my channel. And if you have any question, feel free to leave a comment down there. 73, good luck, bye-bye.